What's up guys? Today we're reacting to a video, specifically PewDiePie's video about Leslie's Doom argument. And I'm going to give a sort of take on what he presents, go over a little bit the argument itself and a few critiques as well, because I think there's a few things that are glossed over, especially in the assumptions. When you deal with complicated statistical things like this, a lot of the assumptions you have to be very careful about. And so I'll go over that and then give my take on the argument as well. So let's get started.
And there are obviously papers disputing these two arguments, but
yeah, so there are disputes for these arguments, of course, and I think those disputes have more warrant than not, so we'll get to that.
So let's imagine that the total amount of humans is n, large n, excuse my handwriting, and this is the total amount of humans to ever live. We're assuming, for the sake of Leslie's Doom, that we will not live forever.
Yeah, so that's an important point, is that there's going to be an endpoint. So that's the first assumption. And I think it's sort of a fair assumption to be made, but it's still an assumption that you're putting in nonetheless. Because if humans were to go on forever, this argument would fall apart. But again, are humans going to go on forever?
And we have n, I guess we can call this your birth rank. Not sure entirely if that's the case, but it kind of works for this.
So what he's talking about with little n here is from the first human, or the first, known human, based on an evolutionary standpoint, to the last human. N is like where you fall there. So like, are you the 1000th human? Are you the 10,000th human? Are you the 100 billionth human, which is what close to we are? So that's like your birth rank.
For the sake of it. Then, if we picture an interval from 0 to 1, where we want to find out n, that seems impossible, right? How can we possibly know the amount of humans that will ever live? We just don't know that. But we can, with a certain likeliness, calculate how many humans will ever live.
So the argument used in this video is based on a huge assumption. And so I have a little diagram here. This is human number 1, the first human, the second human. There's a bunch of humans in between, and then n, which is the last human that will ever exist. And so the assumption here is actually really subtle. And it says that when you are born, you're equally likely to be any one of those humans. So you're equally likely to be the first, second, third, fourth, any one of these, all the way up to big N. Now, it's likely you're not going to be the first few or the big nth, because there's lots in the middle. So you're probably going to be born somewhere in the middle. But the fact that you're born equally likely as anybody is also a huge assumption, and I'll actually get into that at the end of the video. It seems like a fair assumption, right? I mean, if you're going to be somebody, why would you be, one person over another?
So if we assume our fractional position, f, is evenly distributed.
Yeah, so that's where he says it, evenly distributed. And he says it really quickly, but that's, again, a huge assumption. And so what he's talking about with the fractal position here is we're about the 100 billionth, all of us are approximately the 100 billionth human to have ever lived. There's a way that you can think about what's going on here with the so-called fractal position. And so we don't know what big N is, but we do know that we're about the 170 billionth human to ever live. And so that could lie anywhere between, we could be closer to the first one, we could be closer to the nth one, we don't know. We could be over here and, maybe N is 108 billion, that would be really unfortunate. We could be in the middle and maybe it's 200 billion, or we could be really close to here and maybe N is 10 trillion or a bigger number here. Now, because we're equally likely to be any one of these humans, this position is equally likely to be anywhere. We could be really close to N, we could be close to here. Anywhere is equally likely. And so that leads into the next assumption of the video.
We can use the interval 0.05. Let's say that's here instead. So let's say we're somewhere in between here instead. So f is basically bigger than 0.05. We are basically saying with a 95% certainty that we are not the first 5% of humans to have ever lived.
So what he's saying when we're 95% certain is because this is equally likely, of course, to be anywhere, right? The 107th billionth person, which is given by this blue line. The probability that we're close to here, right, is 5% likely. So it's 95% because there's a lot more ways that we can be here. We could be here, we could be here, we could be here. That because this is small, there's a 95% certainty that the ratio of this blue interval to this red interval is greater than 0.05 or 5%, right? If I take the fraction of like this length to this length, there's a 95% chance that it's going to be greater than 0.05 because there's so many ways that we could be out here and out here, for example.
So basically, same thing. Are you falling asleep?
So he writes this ratio little n over big N. I think the easier way to express it is like this. And so I have this blue text here. This is 107 billion. That is our position. That is the number, the human that all of us are approximately. And we can say with 95% certainty that 107 billion divided by n, note blue and red. This line here is blue, this line is red. So the ratio of the blue to the red, that's what this fraction is here, is greater than 0.05, right? And that's because, you know, there's many ways. Like if the blue line was here, it would be 0.9, 0.8, 0.7, 0.5, 0.4, 0.3, 0.2, 0.1, and 0.05 is probably, you know, kind of small here. And so there's a 95% chance that that blue line is going to be somewhere else. So with 95% certainty, this fraction is greater than 0.05. We can rearrange this equation for n and say that n is therefore less than 2 trillion.
To reiterate, we are 95% sure that the human population will never exceed 2 trillion, Edgar.
So it's sort of phrased like it's a fact, I guess. And the biggest thing to take into account, especially in things like math or statistics or whatever, is that the assumptions really matter. And so a lot of assumptions were made here. And so that's like saying 95% sure based on all these assumptions, which I'm about to challenge.
Now, if we imagine that each person lived for 80 years and our human population remains stable at 10 billion, which it currently is. So if we take the...
Okay, so basically what he's doing here is he's saying, well, if there's 2 trillion people that are going to live, you know, what's the birth and death rate, and how long is it going to take us for us to reach 2 trillion?
That have left to be lived. And if we take that times 80, the number is 100. So 15,200 years.
So he arrives at a number of 15,200 years left based on our current, you know, population growth rate and whatever. And so I'm about to challenge a few different aspects of this argument. And so I encourage you to think very carefully about these. So the first thing I'm going to challenge is that we're equally likely to be born anywhere on this line here. And what I would say to this is that you may be who you are based on the characteristics of your time. If your consciousness is based on the things that you like and the hobbies that you have and all the stuff that you do, and that's based on society, then you're not likely to have lived in any other society simply because you are what you do, and what you do is based on the society. And then suddenly it's no longer a uniform likelihood that you're born anywhere. You can only be born in a society that permits you having the traits that you currently have, and thus being conscious the way that you currently are. And so then it's no longer uniform. You would actually have a spike. There'd only be certain places that you could possibly exist. The second important thing to challenge here is a fundamental flaw that's usually made in statistics. And that's calculating probabilities after an experiment has already been done. And that sounds sort of abstract, and I'll explain in sort of simple terms here. So imagine you have a 1,000-sided dice, and I know that doesn't exist, but, you know, yeah, stick with me here. And you roll the dice, and you roll a 5, for example. Well, you could say, well, there was only a 1 in 1,000 chance of me rolling the 5. So I'm 99.9% sure that that dice doesn't roll 5s, and I've rolled a 5. So therefore, the dice is rigged, right? I do the same thing. I roll a 22, and I look at the 22, and I say, oh, well, there's a 99.9% chance it shouldn't roll a 22, and I rolled a 22. So the dice is rigged. And you might think, well, what's going on here? Why is that flawed? Well, the way to do this experiment properly is you have to decide that number before you do the experiment. So if I want to say, like, okay, I think the dice is rigged to roll 5s, I have to decide that before I roll as opposed to after I roll. And that's similar here to saying that we'll be anywhere likely to be the first to the last person born. We've already been born, right? So there is no likelihood involved. We are born, we already have our place on the line. We can't then go computing probabilities about things, and it's similar to the dice example. Finally, there's a third really important flaw to this argument as well, and I think this is the most important one. We're assuming number 1 starts at the first human. Well, what if we start at the first vertebrae? What if we start at the first multicellular organism? What about the first unicellular organism? Suddenly this becomes a lot bigger. And if you do this computation like that, right, suddenly we're no longer the 107 billionth person. We might be the, 200 quadrillionth person. And if I put 200 quadrillion here, n becomes a lot bigger. So it depends. You have to ask when the starting point is, right? Why do we start with the first human? Why not start way back at the very beginning? Are we equally likely to be born as any one of those organisms? Well, there's no reason why one case should be over the other. So I think that's something worth thinking about when you interpret this argument. So are there 2 trillion people that are ever going to exist? Do we have 15,000 years left? I think this is a relatively weak argument for that case, especially based on the third issue that I talked about there, about where we start. If you enjoyed this video, please be sure to like and subscribe. I have lots of Python tutorial videos on my channel. So if you're into coding and stuff, please be sure to check those out. And I'll see you next time.